Now we want to take this piecewise function and cause it to be continuous. Think about the pictures of piecewise functions that you've seen before. Piecewise functions are the ones where the different branches can like do their own goofy little things. So you might have something like, you know, this. This is a common type of piecewise function. They do all sorts of nasty nonsense like that. Let's take this function and insert the value that causes it to be continuous. Consider the piecewise function defined by, for values of x that are at least 1, this is going to be negative 2x squared minus 4x. But for values of x that are less than 1, it's going to be kx plus 1. What value for k will cause f of x to be continuous? We should be able to assign a value for k that makes these two branches meet up. The actual algebraic steps that you take here are that you plug in 1 to both of them. But I want you to understand why, because there's a reason why, and it's worth knowing. What you really want is for the function to have the same limit on the left and on the right at 1. So what you really want is the limit as x approaches 1 from the left of this function to be equal to the limit as x approaches 1 from the right of this function. Because if those two are the same, then the fact that both of these, the first definition, the negative 2x squared minus 4x and kx plus 1, the fact that those are both polynomials means that they are continuous on their entire domains individually. Now, if we make their limits equal, that will cause the two functions to converge at the same point. So yes, plug in 1, but the reason it works is that we want the limits to be equal. But why am I being so finicky about this? It does immediately turn into plugging in 1 to evaluate each limit. Since the functions involved here are polynomials, simply plug in 1. Now I want you to think about it. For x greater than or equal to 1, which one of these limits does this correspond to? This right here means that the first formula is the right-hand limit. Because this is all the values of x that are beyond 1. If you count down to 1 from the right, this is coming from the right, then this is the right-hand limit. Well, on the other hand, this is the formula that will govern the left-hand limit for the exact opposite reason, that these are all the things that are below 1. And so as you count up to 1, you are coming at it from the left. So this one right here is kx plus 1, and this one right here is going to be negative 2x squared minus 4x. Well, now we can just plug in. We've gotten through the theoretical reasons. Let's actually do the problem. So plug in, and you're going to get k times 1 plus 1 equals negative 2 times 1 squared minus 4 times 1. Yeah, I know, it's a bit obnoxious to write the 1 over and over. We're going to get rid of that. So k plus 1 equals negative 2 minus 4. Well, that's negative 6. And then subtracting 1 from both sides tells us that k must be negative 7. So what value for k will cause f of x to be continuous? It's k equals 7. And then for values of k other than the one just found, what type of discontinuity will f of x have at x equals 1? Think about the condition that caused it to be continuous. So for k equals 7, f of x is continuous because the limit as x approaches 1 from the right equals the limit as x approaches 1 from the left. But this was only true when k is 7. For k not equal to 7, now the right-hand limit is not going to be equal to the left-hand limit. And if the right-hand limit and the left-hand limit are not the same, you should be able to identify this is the sort of behavior that we identify with a jump discontinuity. So what type of discontinuity will it have for other values of k? It will have this deserves another color, it will have a jump discontinuity because the branches of the function will fail to meet up.